faster than normal, which is a bit late, lecture 21 already, okay, but, you know, it's not a bad thing. Okay, so, I don't know why there's so few people, but maybe it's because tonight is practical exam, so, quickly, let's remind you that the exam is tonight, okay. The venue is actually PL1 and 2, okay. This one is not free seating, there will be a seating arrangement, we are finalizing it. We'll be posting it online, but once we finalize the seating arrangement this afternoon, okay? And then, of course, you have a list there, you go there. Don't come at 7 o'clock, come at a bit earlier, 6:55 or something. Okay? Then we make sure that you can tell you which room you go to. Probably going to be some kind, okay, we'll probably do by vertical order, probably, okay? It means, except that we need to know where to split the half the class, okay? So you probably end up in a room depending on your last name or something, or first name. Okay? So there will be 4 questions as normal. The real exam is consists of the first 3 questions. So the deal here is that the first 3 questions are not that hard, because that's the real exam. Okay? The whole point here is to test that you can actually solve reasonably, I won't call it challenging, but reasonable questions, right? So basically, if you can solve the first 3 questions, you have an A in the class. Okay, if you get something like 27 to 30, because you should be able to, you're expected to be an A student, you expect to solve the first 3 questions. Okay, you expect to make some mistakes, right? So you can get like 27 or something like that. Okay, so the point here is that for each question there will be some like sample test cases, right? But obviously those test cases are not complete, right? Okay, as per normal. So if you pass, first of all, if you don't pass those test cases, you're in trouble. If you pass all the test cases, you may still have mistakes, because you may have other test cases. Alright, so then the last question is for fun. Okay, let me tell you the history. If you do the past year exams, you realize that 2006 is much easier, right? What happened that year was, okay, so I have XTA. Okay, he was a top student that year, and he finished the exam in half an hour, and he was writing Pokemon and Friends adventure game. So I was like, what the heck are you doing writing Pokemon and Friends adventure game in my practical exam? So I thought, hey, this cannot be. So from then on, in 2007 onwards, we created question 4. So the point here is that questions 1 to 3 is a proper exam. Question 4 is to soak up all the rest of the time for whoever is very free and finish the exam in half an hour, so that he doesn't go out, tell the whole world that, oh, I'm so great, I'm so smart, right? I finished Ben Long's exam in half an hour. Okay? So that makes the exam long enough for everybody, okay? And then the good news here is that basically the exams are 30, which means that you score full marks for the first 3 questions, you have full marks for the exam. Excess points for the exam will go to the midterm exam. Okay, so this allows also people to make up for basically having brain damage during midterm. Okay, and essentially quite a number of students in this class will likely have full marks going into the final exam. Okay, but it's okay. Final exam is already set. Not so easy to get full marks, okay, I suspect. Alright, and what else is new? Okay, so if you feel lucky today, you can do one of questions 1 to 3, just do number 4 and you're done. Okay, so because the last question is worth 20 points. So solving that and one of the first question is sufficient to finish the entire exam. Okay? Why is Jen laughing? You're trying to do that tonight, is it? Okay, that's fine. Okay, so, okay, and as per all exams, you are, okay, so the interesting thing about practical exam is that, frankly, okay, let me tell you a story. I also don't, actually I don't mind open book, open everything, okay? But I was very kind like 3 years ago, and I said that you bring anything you want, bring thumb drive, whatever, because I actually don't care. Okay. Actually, that was a terrible mistake, because when I let the students bring thumb drive, right, there was a student who was very conscientious. She prepared a 10 KB like cheat sheet thing, but the cheat sheet is actually in code. And she basically took the whole thing and copy and paste. So I have this, okay, the exam submission is there's not that much code. It's supposed to be like 2 pages of code. Then bam, she take the whole 10K, put right smack in front as a preamble to her answer. So I'm like, damn, 10K doesn't sound a lot, but it's a lot of text. Okay? And then the thing is that here, okay, so the deal is this, obviously life is good if she has perfect answers, right? It means I run out of test cases, all clear, full marks, right? Well, she didn't get full marks. Okay, so there, okay, and then the problem here is this. If you get full marks, then your answer is full marks, very easy to grade, no. If you don't get full marks, the grading scheme is very simple. The grading scheme is the right answer, that's your answer, and I'm trying to figure out how far your answer is from the right answer, okay? And can you imagine having to trace through 10K of text to figure out how far her answer is from the right answer. So that was not fun. So for my sanity, I decided I cannot. So you are supposed to type out every single thing you submit to me. You can type out, I can read. Yes. Because it is possible some people need to write a lot of code, right? Yeah, but that's a good idea. But anyway, I didn't realize that, okay? After that, I realized that it was a stupid idea to give people the thumb drive. Because truth of the matter is that you shouldn't need a thumb drive. Okay, if you know what the heck you're doing, the total amount of time taken to type out all the answers to the exam is like 5 minutes probably, maximum 10 if you're slow. Okay, so the total amount of code required, okay, so if you're damn fast, you go in there 10 minutes, you type, finish, you're done. You typing alone, I'm sure you're typing alone 10 minutes, finish. That's if you don't have to test, debug, don't have to think. Okay, so the total amount of code it can take you no more than 10 minutes to type. Okay, maximum. So therefore, there's no reason for me to let you go and basically import the whole thumb drive. Okay, so anyway, that was for my own sanity. But you can bring any kind of printed material, anything that doesn't run on electricity. So thumb drive cannot. Okay, clear? All right. Yeah, and then also, okay, you will have access to IVLE. Okay, first of all, also you want to be a bit green. Okay, because we don't want you to start printing the whole entire. There's a lot of stuff at 1YS, a lot of stuff. So you print everything, also you kill a lot of trees, right? So to make life a little bit easier and environmental friendly, you have access to IVLE, which means that you can actually look at all the passing exams, you can look at all the solutions, look at all the lectures, whatever it helps you to sign. Okay. Now let me tell you this: if you spend the whole entire exam 2 hours trying to find stuff to apply, good luck to you, Okay. So the moral story is hopefully, in theory, you should be able to go to exam with nothing, okay, and be able to solve from first principles. Okay, my exams are all first principles based exams. That means you can know nothing, have no code, whatever, and solve. In theory, okay. Now, if you want to use obscure scheme libraries, you carry on, okay. But if you get it wrong, then you're in trouble. Questions. And finally, if you have an idea how to solve the problem, but you can't really get it done, you may write a little short essay. You get 0? Yes. I pretend I can't read Java today. Okay. So any questions so far? This class, by the way, this is a scheme class mostly. Java is for fun. Okay. Okay. Okay, so this is again, you bring anything you want. Okay, you bring the entire library if you want, as long as it's not electronic. Okay, obviously you can't be, doing talking to people in the handphone. Okay, then clickers. Okay, so all you can take out the clickers for one last burst of fire today. Then tonight, what we do is that you collect the clickers back. So tonight, like NUS exams, you take out a clicker, put at the top left hand corner of the table. Okay, Joe Chi will come by and collect all the clickers. Okay. If you forget, obviously you have to work out with Joe Chi how to return the clickers. Okay. So Friday. Okay. So basically, after tonight, a lot of people are very frustrated. So maybe, okay, or maybe Val is very excited. So Friday we will have a real lecture. We will actually have the DevQ contest. So essentially, okay, those of you who are too lazy to do more, you can just submit the Mission 19 submission and get killed. Those of you who really want to basically let out steam or something, you can spend the next 24 hours hacking your Mission 19 bot, okay, so that you can basically take out some people on Friday. Okay, so basically, yes. Yeah? No, the rules are clear, right? You have 10 points for the bot and 5 points for anything. I forget what the rules are. I mean, weird things happen, okay? So I don't know what you can do, okay? Alright, but anyway, there are rules to the contest, right? Okay? I think you can kill other people. But the problem is that once you start shooting your fellow players, right, then you get labeled as a bot or as an enemy or something. Then all the other guys, typically the whole point now is that the engine will look for a bot to shoot, right? Yeah, but and then basically you become the enemy flag, and then all the other players in the same map will also shoot you when they assign you. Fun, right? Okay. Questions? Okay, anyway, this is a Friday. So Friday is kind of cool. I hope, I'm conscious to attend. No real, okay, you don't have to attend to them, but it's really quite cool, okay? It's basically you project all the DevCube things, then you see basically your bot, basically shooting bots, shooting other players. It's kind of cool. Alright, questions? Okay, so it's Friday, yeah? This is the after PE kind of chill out day, okay? I don't know how long it takes for me to grade a PE. Okay, obviously if all you are so good, all right answers, wow, very fast, okay? By tomorrow, all done already. Okay, but then the length of time taken for me to grade depends on basically how many mistakes people make, right? Okay, so you see, if everybody gets 2 marks, which I'm quite happy because that means I'm a good teacher, right? Then, you know, we'll be done by tomorrow, okay? But if not, then you take probably 2 days, okay? So hopefully, I try to clear this soon, okay? Hopefully I can clear this by Friday, if not Saturday, okay? All your PE. Okay, so anyway, today's agenda is the following, okay? So we will talk about all these things in Java. So, okay, this is a terrible lecture to give. Because most people are probably doing ski or something, trying to prepare for the next PE. I don't blame you, okay? But anyway, you can try your best to pay attention, okay? And if you don't, then it's not my fault. Okay, so first we take out the clickers for this. Now, let me explain to you why I'm so fussy about these loops. Okay, this is actually a quick story. What happened was the following. Okay, what happened was that, okay, a few years ago, I realized when people went from skiing to Java, right, they don't like loops. They basically do recursion for every single thing. So I'm like, okay, then basically it makes me look like a moron, no? Like my students teach already this sort of thing for Java. So it was not funny, okay? So okay, now, so as they say, right, when you go to Rome, right, you do as the Romans do, okay? Okay, this is how the Java people do loops, okay? They don't typically do recursion, okay? So now let's quickly go through this. I think Ali went through quickly this loops for you last Friday. Let's quickly do this, okay? So how many lines have you printed? Hey, take out the thing and click. Sorry, I haven't finished yet. Okay, this one is, what is this again? Plus? Okay, you add 1 to val, okay, very good. Okay, so now we can all click. Eh? Why is it not working? Oh no, why is it not working? It's broken. Okay, terrible. Hey, what happened to... Oh no, there was supposed to be the clicker thing. But let me make sure that this thing is... I did put in the... How come the clicker thing is missing? There, the clicker thing is here. Okay, let's try it again. Turning point. Reset section. Okay, let's try again. Ta-da! Hey, it's broken. It's terrible. Okay, so sorry. So the last burst of fire. Okay, so apparently the clicker thing is not working today for some strange reason. I thought I did this properly. Okay, maybe I try again. I insert the... Should be a clicker. No, it's not working. Let's try again. Close the window. Open. Oh wait, is this the read-only problem this time? Wait, Open the read-only copy. Why is it being used? Being modified. Okay, hold on a sec. Task manager. What is modifying what? I don't understand this. Let's try again. It fails to work lah. PowerPoint. Original function. Which one? Okay, I got it. They're right. Okay. Okay, that's just. Okay, maybe it's because it's not writable. Hold on a sec. Okay. Let's try this again. Open this one. Okay, that's how it works. Okay, it works now, okay. Whoops. Okay. Cool. Okay, it's because it was not writable, so somehow the thing prevent writing. So once you can't write, then you can't save the session. Okay, so now quickly. 18, how many are you here? 2, 4, 5, 10, 15, 20, 25, 30 only. I'm missing 10 students. Okay, 30 are you? How many speakers? 5 missing, is it? 26. How many are you? Anybody? Ready? 27. How many? We all ready. Hey, how many of you have speakers? 4, 5, 10, 15, 20, 25, 31. How many don't have flickers? 4 don't have flickers, right? 1, 2, 3. Okay, whatever. 27. Answer is. Ta-da. Okay, who are the two fellas? Okay, how many are there? Okay, so the answer is what? 10, right? Because, okay, so what's going to be printed here? Okay, first you print what? 0, or the value is 0, value is 1. Why? Because you start with 0, right? Once you go into loop, right, you plus. Okay, so the first thing you print is 1, right? Okay. Then after you go through 1, 2, and so forth, at some point you reach 9, right? No, 9 first, right? Before 10, right? So 9 you go through, you see val. You see val is what? Val is 9, so val is less than 10. So you go inside and you print 10, right? So you're printing what? You start with 1, you add with 10. How many pieces? 10 pieces, right? Okay, so answer is 10. Okay, next one. How many? How many lines? 9, 10, 11, or none of the above. Fourteen, set up, rest. Ryan, do you have a clicker? You have, right? Okay. Hey, 2 more. Who's the last 2? Okay. Okay. So the thing to note here is that the block. Okay. What's the difference between the do while and the while loop? Okay. So the while loop will check for the condition before it goes into the loop. Okay. Do basically will go to do the loop. Will do the block at least once. Okay, and then check to see where it restarts again. Okay, so here basically your block is valid at least once. Okay, first time, what do you print? First time you print 1, right? Okay, then it keeps going on until what? Until you print 9, right? Correct? Then after 9, you still go back. When you go back, right? Then you print 1 last time and then you close. So the answer will be. Ta-da. Okay, so how? Okay, the answer is 10, because you have to basically go back one last time. So you actually be, okay, so the point here is that you must make sure you mentally go through the loop a few times and see how it works. So the answer is 10, even though it looks a bit different. Okay, for loops. Okay, this is very simple. Okay, so the first two are the while loops. The while loop has two forms. The while loop itself and do while loop. Okay, so this one is actually the for loop. So the for loop is of the okay, like this is a very standard kind of, this is a very standard idiom whereby you always kind of do this. Okay, you can declare anywhere you want. Okay, so Java, unlike C, actually C, the new version, can also declare anywhere, I think. Only my time, then I forced to declare our variables ahead of time. Huh? The new specs of C, you can declare anywhere, I suspect. Okay, anyway, Java definitely can declare anywhere, so this is the declaration. Hey, 5 more. How many lines? That is quite straightforward. How many lines? Who are the last 3 fellas? 28? There are 20 of you in this room. 2 more. Okay, very good. Okay, so this one is, wow, what happens? Okay, so this one, okay, what happens is I, okay, what is the value of I in this case? Starts on what? Starts 0, ends at 9, Okay, so I will range from 0 to 9. Okay, you print 10 lines. Okay, so next thing you know is basically how to break out our loops. Okay, let's break. Stops the loop. Okay, so break actually breaks out the loop. So the question here is how many lines we printed in this case? Because I think you're not that stupid, right? Right? Sorry? Oh shoot, I think it's a problem. Oh, it's okay. Alright, okay. Are we okay? Hey, hurry up, 3 more, last 3. Yoo-hoo. Huh? What problem? No, there's no problem. Last guy, who's the last guy? 28. Yoo-hoo. Hey, can you all quickly press now? Make sure you did press the thing now. Oh, waiting for this one last guy. Hey, yeah, don't press user feedback. Press the right button. Please make sure that when you press the thing, the thing increments. Can you all press now? Hey, one guy is missing. Okay, very good. Okay, voila, what's going on? Okay, okay. So the point is this. You want reason about this? First thing you do is this. I is what? I starts at 0, right? You go in there, prints there, value is prints 1 hello, right? Okay, you increments until what? So you print hello 1 time for I is 0. 0, 1, 2, 3, 4, right? So how many times is that? 5 times, right? Then when you reach I is 5, you will break out a loop at n. So the answer will be 5. Okay, continue. What does continue do? Okay, continue basically skips the current one and returns to the beginning. Okay, skips the current iteration. Okay, so what's the answer here? Well, Yi, you got questions about the previous one? Okay, right. Hey, 2 more. Okay? One more, one last one. Who's the last guy? Yoo-hoo. Okay, very good. Okay, so what's the answer? Okay, wow, all very good. Okay, so, okay, what happens here? Okay, why is it 9, not 10? Okay, because, okay, originally, remember, this is a for loop, right? This for loop has 10 iterations, right? So originally, you print 10 hellos, correct? Okay. Now, what happens here is that when I is 5, okay, what happens when you continue is that you go back to the beginning of you go to the next iteration. So basically, you skip 1 hello. So in the end, instead of printing 10, you print 9. Okay. So okay, so this is pretty much an overview of the loops. Okay. Now, so the moral story is this. Okay, these loops are not very hard. After all, you figure it out. The moral story is that in Java, please do not use recursion to do this kinds of. Okay. So if you want to solve problems using iteration in Java, please use loops. Okay. Do not use recursion. Okay. Recursion in Java should only be used to solve recursive processes. Okay. To write recursive processes, you do not write iterative processes in Java using recursion. Okay, but the only thing to be aware of is that, okay, remember the 2 weeks ago we showed you this what's that, the Fibonacci, right? So the nice thing about doing iterative processes using recursion is that you can do simultaneous updates. Remember? So the A plus B can do at the same time, right? So the only thing to remember is that if you're doing iterative processes in Java using loops, you may have to basically create temporary variables to not overwrite things. Okay, that's the only thing to remember. Okay, so basically recursion is kind of cool, but in Java you will almost never see recursion. I have only written recursion in Java like once or twice in my life. Okay, most things actually you solve naturally using loops. Okay, so now there's another thing. Okay, so there's this particular syntax you should know for Java, which is this syntax whereby it's for something. Okay. So this is actually a for each syntax. Okay, essentially you declare a variable here, you have an array, you can do stuff. Okay. So what this will do is that, Richard, what this will do is that it will actually iterate through all the elements of the array from the first one to the last one. Okay. But obviously this doesn't have to be done because what you can do, there's a typical idiom which is what? For I equals to 0, okay, semicolon, what? I less than array.length, semicolon, I plus plus, then you can do the same thing. So, but this is something you can do if you, and this syntax will also work for lists and other collection objects. I'll talk about collection objects very soon. Okay, so basically this kinds of for each loops actually work. Okay. It's like for variable like int x or something like that. No. So then there is x is the okay. I think we have the example, right? Okay, no example. Okay. So the idea is this, right? Okay, in the Java, okay, in scheme is for each lambda x do something on a list, right? Correct. Okay. So this one is actually for each. You need to give the in x. The x needs to be fed into from the array. So the x must be the same type as the array. Okay, and then you basically do stuff inside here. So think of this as lambda x here, the stuff inside here, and then this is the list of the array. Okay. All right. Okay. So who actually did this? You were supposed to do this, right, for practice. You did, Okay. Who else did? Okay. So anyway, up to you, Okay. So the point here is this: okay, in this class, all the problem solving is taught in scheme. Right. So your final exam has 15% Java, but really it's actually scheme pretending to be Java, right? Okay. So the whole point is that the questions obviously can be solved in scheme. The question here is, can you do the translation from scheme to Java? So basically, doing this stuff is practice for translating stuff from scheme to Java. Okay, because you will have the transition to Java next semester, so might as well start easy. And also the problem is that basically I told you last week, right? There's too much. Okay, if I keep doing more scheme, actually there's more scheme design. SICP has another 2 chapters. Okay, but unfortunately, if you do another 2 chapters for the last 3 weeks, basically basically we have enough time to cover the stations and discussion groups it's a problem of fitting stuff. So now the last 3 weeks of Java is meant to be a bit more free and easy. It's an intro to the next semester. Okay, your main goal is to learn syntax and have some basic understanding. Okay, all right. So the way you should think of the final exam is that you are solving the problems in Scheme, except the only thing you need to learn for Java is the translation from Scheme to Java. So it's mostly syntax. Okay. So Factorial. Okay, so let's quickly go to this. So these are the 2 versions of Factorial that you have obviously seen in Scheme. If you can't do this in your sleep, then you're in trouble tonight. So I assume you can. Okay. So first of all, we look at the first. This is the what version of Factorial? Iterative recursive, right? So this one you can do in your sleep, right, like that. Okay. So the question now is, how do you do this in Java? So the problem with Java is this. Okay, is that every single thing requires Java is object oriented, but that makes it annoying. So because the point now is that even if you want to do something simple like this, all you want to do is compute Factorial. You actually have to create an object. Okay, so I have to create this thing called a Factorial object. Okay, call anything you want, but you have to create an object. Basically, a class. You can create a class in order to do Factorial. Okay, now actually what I'm doing here is this. So notice this Factorial, okay, is actually static, right? What does it mean? It means that this is actually a static method, which means that it is a method of the class, which means that I don't have to create a Factorial object in order to call the method, which is kind of annoying, right? Okay, so basically what happens here is that, okay, you look at translation, okay, if n equals to 0, 1, so if n equals 0, return 1, very simple, okay, otherwise you do what? Otherwise you do star n factorial thing, so you do return n times factorial this, okay. Only difference here obviously is that is this postfix infix things, right? Wrong, prefix infix thing, right? So from prefix you move the thing in middle and you're done. Okay, so this is as far as it goes. Very simple. Questions? No, right? Okay. Now next, so this is static. I said it already. Okay, so this is the facty. Facty is what? This is the iterative version of Factorial, right? Again, you look at it. Same thing. Okay. Essentially, you look at translation. Okay. So first of all, okay. So you see, this one, this thing will be a what? Recursive call, right? Okay. Obviously, I just said, right. Do not solve iterative processes using recursion in Java. Okay. So essentially, you need to do the same thing here. So what I'm doing here is okay. At some point, okay. So this one doesn't kind of, this one doesn't. Oops, I think there's a problem, right? What's the problem here? This one, the Java, the scheme code is actually wrong, right? Because I multiply at 0, the whole thing will blow up, right? Is that right? Then the result will be 0. Okay, so obviously there's a bug here which I didn't realize until now. Okay, but the point now is that you can't translate this quite so simply. So you need to look at this thing. What I'm doing is this: I set value to 1, well the result, okay, and then I do a loop from 1 to n. Okay, and then I do okay. So why did I do from 1 to n instead of 0 to n? 0 to less than n. Okay, the thing to keep in mind is this. This thing is important. Right, the sign here less than equal makes a difference. It's different to one element. Okay, so typically most times you do I equals 0, I less than n. Here I do I equals 1, I less than equals n. Why? Well, because I'm multiplying this thing in, right? If it's from 0 to n minus 2, 0 to less than n, I will multiply by I plus 1, right? Okay, so anyway, the point here is that it starts with 1, and then I go in here, I will do n times, multiply in the index, which is from 1 to n, and then I'm done, return the result. You can do whatever way you want to do. I mean, there are many ways of doing this, right? Perhaps. Okay, but the key thing is to realize that you can do this loops. Okay, I thought there's a mistake here. Okay, now so next thing, exponentiation looks like this. Okay, you should be familiar by now. Okay, let's take a look at the first one. First one, okay. Again, I create a class. Okay, this is the simple version, which is the recursive process one. Okay, and essentially the translation is almost direct. Okay, so okay, the thing to realize for Java is that you need to have you need to declare a type for the method. You need to declare types for the inputs. right? Okay, so if e equals 1, e equals 0, you return 1. Otherwise, you return what? D times power of this thing, which is this. Now again, this is a similar thing. Okay, so for this case, I'm multiplying. Okay, for this case, what happens? I actually don't care about the index, right? What index does is that it goes from 0 to less than e, which means that it goes from 0 to e minus 1, which means that e times. Every time it loops in there, I multiply by b, right? Okay, so essentially I'm done here, okay? Alright, any questions so far? Okay, so this illustrates, anybody has any questions? Why? Looks bad, they are. I think that's okay. That's for practice, because the point now is that if you are supposed to be a Java programmer, you write the kind of loopy things in recursion, it looks kind of bad, okay. I'm not sure about. Okay, so scheme does tail recursion. I'm not sure how it's implemented in Java. I think you actually don't have that. You will be pushed into the call stack, so it's going to be very deep. Right. So anyway, the point is in Rome, do as the Romans do. This is how Java people write the loops, okay. And you shouldn't try to. Okay, I don't know about 1010 doing recursion. Maybe they're trying to teach them recursion because they don't do enough recursion, right? So for you, you're doing enough recursion. It comes out your years, right? So don't have to do so much, right? Okay. All right. So too much a good thing is often a bad thing. All right. So for Java, just do it the Java way, okay. So it's actually it's quite simple, right? To be honest, okay. Okay, it's hard to explain, but then every language has its own kind of style, alright. And if you try to, okay, so I have students writing scheme. Okay, this semester okay. I haven't seen any really bad code, but there was a semester whereby the student was obviously writing C code in scheme. Okay, and it's not a good thing, right? So you shouldn't be writing scheme code in Java either, alright. You basically should write code in the kind of style that is kind of natural for the language that you're working with, so that people don't get confused. Okay, that's very rare. Okay, so obviously, if I look at scheme code that's pretending to be Java, I can understand the scheme code pretending to be Java because I'm used to it. But people who don't do scheme will be like, what the heck this guy is doing? Alright, so it's a problem. So the point now is to understand that oftentimes the code that you write is not just for you. Somebody else has to read it. Okay, so try to do it in a kind of conventional way. Okay, the next thing, this is a quite important idea. Okay, so we've done this before. This idea of equivalence and equality, okay. So the point is, identity basically means what? Same object, right? Okay, in scheme is checked using what? EQ question mark. Okay, in Java is checked using the equal operator and the bang equal, which is not equal operator. So Java doesn't have what? Doesn't have the not, right? Correct? Okay, so the not in Java is the exclamation mark. Okay, so basically this means that these objects are equal, identity. Okay, identical. This means they're not equal. Okay, so the EQ. Okay, and this essentially tests out whether the two variables are in the same location. Okay, now equal should be used. Yeah. Okay, so there are two kinds of objects, right? There are the so-called the primitive objects. Not objects. There are two kinds of there are two general classes of variables, right? There's the primitives and there's objects. Okay. So for the objects, you essentially use equal to test for whether they're the same object in same memory location. The primitives are okay because primitives they are all equivalent. These are the same. Okay. Now, so there is also the equal operator, which is the equal thing. So the thing is that remember that all objects in Java inherit from what? Object. Okay, there's nothing called object, which is the base class, right? And that particular base class supports this method called equal object. Okay, and basically by default it's equal to equal. I mean by default equal is equal to equal, right? I mean this equal to equal, right? Okay, so this is by default. Okay, so the point here is this: when you define new data types, okay, it is important for you to go and define to override this equal operator. Otherwise, all things go haywire. Okay, let me show you the example later. Okay, so for example, okay, and then there's another thing. So this is a bit subtle and it's a bit advanced, but you should know this before all things blow up. So basically, when you define a new data type, right, you need to override equal. There's also another thing you need to override, which is a thing called hash code. Okay. Basically, if you don't do hash code properly, the collections objects will do the wrong things. Okay, let me hold on. I'll talk to you about this later. Okay, and also there's another function that you should try to override, which is called toString. Okay, toString is the method that's called to print the string representation object. Okay, later I'll show you an example. Okay, so let's take a look at this. Okay, suppose you want to create a new object, very simple object called vector. This is a 2D vector. Okay, essentially it's just two things, x and y. Okay, and it's integer, so very simple. So it's actually this kind of like how you define the the object. Okay, interesting to note is that there's this thing here, which is what's going on. Okay, now what's happening here is this: the input arguments to this constructor actually shadows the internal variable. Okay, so the way to do this, the reason why I use this basically accesses this object. So this dot something will access this two variables. Okay, if you just do x and y, it will actually be the arguments that's coming in. Okay, now this is a kind of general convention although there's the shadowing here, but the shadowing is actually deliberate. Okay, otherwise you end up having different names for different things. So this makes it simpler. Okay, question. Okay, understand? I say again. If you use this case is if you use x equals x makes no sense, right? Because the x will be the incoming x. What I need to do is to use this dot something so I can access these two variables and set to the x, which is the incoming argument. Okay, now next. Okay, so this is what I do. Okay, now the thing to understand is that the way Java works is the following. Okay, you need to have a main. Okay, you can run a class, right? To run the class you must define this main function, which has the following kind of declaration, like public static void main string arguments. Okay, so essentially if you define this particular method, static method inside any class, okay, you can then run the class sort of. Okay, so in this case what happened is this: I created two vectors v1 and v2, right? Okay, both of them are 1, 1, right? Okay, system out.println is just to print. It's just like display in scheme. Okay, now so I do two things. First of all, I print out v1, and then I print out v1 equals v2. Okay, what's the expected answer? Sorry? So, okay, what you want, expected answer is that what you want. You want the first thing to print 1, 1, right? So you can see what the vector is, right? And the second thing you want to print is what? You want it to print true, right? Because v1 and v2 are the same vectors, right? It's equivalent vectors, correct? Okay, but obviously in this case it's not going to work out. And this is what you get. Okay, you will get this thing. The first print line will print this thing called vector something something. Okay. Okay, okay, actually what I call it vector naive because in the actual code I give you is not called vector. Okay, and the second one you get false. Okay, now why is this happening? Well, because the problem here is this. First of all, when you print out, okay, what happens when you print an object? Okay, what happens is that this print function will go and call the toString function of the object. Okay, the default toString function, what we do is you print out the name of the class of the object and some random string which somehow is, I think, related to the memory location of the object. It doesn't really mean much. Okay, and the second thing is this: the equals function by default is what? It's equal, right? So basically the two pieces v1 v2 are not equal because they're different objects. So you get false. Now, so how you deal with this? So first of all, I will override the toString using this thing, right? Essentially, so I do parentheses x plus comma y close parentheses, right? And then the thing, okay, what is this thing? Override. You know what it is? Okay, this funny thing whereby it's an ampersand, it's an add and something. This is known as annotations. Okay, so it doesn't actually do anything per se. Okay, what it does is that it hints the compiler, okay, that this particular method you define must override a method in the superclass. Why do you do that? Don't you know you have to override an object in the superclass? No, but why you want to use these annotations? You know? No, okay. The main problem is the following. The main mistake that often made is this. Superclass, you know there's a method, okay? The method is a superclass that you want to override. You know that for a fact. The problem is that you don't type properly. You typo. Okay, imagine. So the whole point is superclass has this method you want to override. In subclass, you want to override the superclass. But you that day, I don't know what, drinking or something, drunk, so you typo, extra R or something like that. Now, the problem is that you do that, is it okay now? It's perfectly fine, no? Because, it's just different. The compiler has no way to know that this class is supposed to override that class. You typo it, what happens? There are actually two methods, right? There's a method, there's the original method, and there's a new method which is misspelled, right? Now, obviously, when you type code, I'm doing the new overridden method, right? But actually, you always find the old method, right? You have no idea, no? Okay, so it's very nasty. It's a very nasty problem, okay? So the whole point here is this. What you do here is that you are actually typing this thing to tell the compiler that this method is meant to override a superclass method. Now, if the superclass method doesn't exist, it will complain. So this will basically prevent, is a way of preventing typos and hatching mistakes. But it doesn't do anything as far as the program is concerned. Okay, so these annotations are actually ignored. Okay, so first of all, I overrode toString to give you this thing. Yes. At lah, like email like that. At. Like emails. Your email at, right? Okay, so it's the email thing, symbol, so it's an at. I just explained, right? So the whole time I was explaining, you're trying to figure out what the symbol is. Sorry? Because if you don't have a symbol, then that thing is called is interpreted as a modifier, which will cause error, right? Because the problem is that the at tells you that this particular keyword after that is not a modifier; it's just an annotation. So the compiler will actually ignore it generally. Okay. If you don't put it, then override becomes a modifier, but it's not override is not a Java modifier, right? So okay, so these are modifiers, all these things. Okay, this is a modifier. This is actually this is the type declaration, and this is obviously the method name. Okay, so this one is again, this is the equals method. Okay, what I do is this. So the method, the object comes in. So it's actually I'm going to compare with another object that comes in, right? So generally, what you do is the following: you use this instance of. So it's actually you check whether the object coming in is the instance of the current class. If it's not completely, obviously it's not equal, right? No way in hell it's equal, right? Okay, so the first thing you do is that. Now another thing is this. Another thing is that the thing that comes in is the object, which is the object, right? But it's very annoying to deal with object because then the only way you do is that you cast the object. Okay, first of all, if the object is not the same, it's not a type of the current class, using instance of, you know it's not equal. Now, if it is true, then you know that the object coming in is actually a type. It's actually an object of the current type. Then you can cast it into the current type. Okay, now why would you want to do that? The reason why you want to do that is that once you can cast it into the current type, right, you can then access the objects or the variables inside as if just using dot notation. Then that allows you to compare. Okay, so this is a general. Okay, so that what I'm teaching you is this particular method declaration is what you call the so-called canonical form of this equals. Okay, you can do it differently, but try not to be too smart. No creativity necessary. Okay, you just follow this convention and typically you do right things. Yes? You cannot do, because O is object. You do O.x, the thing will blow up and die. Because O is an object, the object O doesn't have the X variable. You have to cast anyway to some extent, but you cast it this one time, it's much easier on long run. Because in this case, very simple, only two states. Some objects are very complicated, has many states. Then you basically have to keep casting. So this is a simple way of doing it. Okay. And these things are quite important. Do pay attention. Okay, you may not have to know this by by heart now, but make sure you kind of understand this thing exists. Okay, so that next semester when you do Java again, you can review these lectures and then you figure out what the heck's going on. Okay, now these things can lead to very nasty mistakes. Because the problem here is this, equality is a very important operation, right? You oftentimes compare two things equal or not. Okay, equality, if not done properly, very hard to test, very hard to debug. Okay, just trust me. Okay, what these days, if you don't understand this and never make mistakes, very good. One these days you forget this, you get burned. My God, you understand what I'm saying. Then you know, wow, I shall listen. And you understand what this is about. Okay, basically equality bugs are very hard to if you screw up equality, you can have very nasty bugs that are very hard to debug. Okay, so it's important to understand. Okay, hash code essentially is you have basically what you do is you multiply some prime number to all the things and try to hope that they're different. Okay, so okay, I will not go to hash functions because next semester you will learn that in 2020. But just know that you will have to do this properly. Hash code and equal, they go together. Okay, I'll talk about this in a little while. Okay, so after you fix these things, when you run this same code, you get this. Okay, the print line will print 1 1 because you overridden to string. So you print out this representation, which makes sense, and this equals will now print true. Okay, so this is good. Okay, so hash code is basically for something I'll tell you. Okay, hash code, I'll talk about this in a short while in terms of the object collections framework. Now the thing is that, okay, I think I'll leave it later because it's very complicated now. Okay, just carry this hash code. Just know that hash code and equals, they come in pairs. Okay, now just quickly before we continue, there's this thing called the count change, right, which you know. Okay, essentially this is the problem, right? You take some money and then you want to go and break down into denominations. How many ways to do this? Okay, so this is the code that you saw in Scheme. Okay, alright, the question now is how do you do this in Java? Okay, and okay, so this code in Scheme, this is the Scheme code here. So again, count change can be done in the following way. You look at the translation, it's almost 1 to 1, right? Amount 0, 1, return 1. Okay, amount less than 0, kind equals 0, return 0. And then count change, basically the recursion over here. Okay, this recursion is just written here. Okay, quite straightforward, right? Which one? There's no third line else, what? Yeah, you don't need the else, that's true. But it works. Okay. Now, so the thing is that you have this lookup table which you can use a switch. Okay. This switch here is equivalent to the case statement in Java in the Scheme. Okay. So essentially what I'm doing here is that remember this lookup table to check what the denominations are. I can actually basically do a switch on kinds. Okay, and I can do this. Okay. Now the interesting thing that Java has that Scheme doesn't have is this thing called exceptions, which we'll talk about next week. Okay. But what happens here is that basically we'll go down the list and then there is a default thing. Okay, basically default means that if you can match them, it's good for you. You can't match them, then you will go to this thing, which throw exception essentially tells people that something's wrong. Okay, we'll talk about this exception next week. Okay, so remember in the iterative form of count change, right? The idea is what? Use a queue to go and keep track of all the nodes, right? Okay, so how do you do this in Java? Okay, so this is the algorithm, right? You create a queue, empty queue, you put a node inside the queue, then counter set to 0. Then what you do is you take out one node at a time and you deal with it, right? If it's a good node, you basically add 1. If it's a kind of a failed case, throw away. If it's a kind of an intermediate node, you generate 2 nodes to put back into the queue. Right? This is the general idea. Okay, so this is count change. Right, this is the code that you saw. Okay. Now the way that we do this is the following. We need to create a node. So the problem here is that in Java you need to create objects. Right. So you notice over here that essentially you have, you basically have these nodes in the tree. Right. Each node stores 2 things. Right. The amount and the number of types. Okay. So what we can do here is we can go create this nodes, which is this objects. Okay. Same way. It's very standard. The class declaration. This is the internal state, and then this is actually the constructor. Okay. Okay. So the question is how about the queue? Okay. It turns out. Okay. Now I'll talk about this. It turns out that the Java, there's this thing called Java has a lot of libraries. A lot of libraries. Okay. There's this thing called the collections framework, which is actually a library that basically takes care of most data structures you can imagine. The lists, the queues, the stacks, all those things. Okay. So essentially you need to. So essentially the point is that you must go and find this thing and use it. Okay. And the Java queue interface. Okay. So the interesting thing is this. What Java offers, there's this thing called interface, right? Interface is what? It's actually a collection of methods. Okay, so for Java they call methods, right? Functions is for C. Okay, now so the point is that there's this thing called the queue interface. Okay, and it turns out that if you look at this, okay, so what is this? This is a page from where? Java docs. So it turns out that the Java documentation has a certain kind of format, right? And what the Java documentation really is actually a whole bunch of interlinked HTML files. Right, so all these are links. You can click next class, previous class, whatever. You can start traversing the whole thing. Obviously, you can search also. All right. So the whole point now is that for this queue, okay, interface queue, okay, the queue basically supports some super interfaces, okay, which are collections, okay, and then the sub interfaces which are blocking queues. And also the interesting thing is that there are many classes that implement the queue. Okay. So the thing is which one is the right one, okay? Now, and the queue interface has the following methods, okay? This is very simple summary. First is element, okay? It actually retrieves, okay? It's actually the peek operation. You look at the top element of the queue. Offer basically inserts an element to the queue, okay? Peek, what's the difference? Peek and element. Okay, so peek element, they do the similar things. Except returns null if the queue is empty. Okay, and then poll basically removes the head, okay, and retrieves it, and now it's empty. Basically removes the head without returning it. So these are the kind of the methods that it supports. Okay, and then obviously it will also support all these elements from collections, which is that you can add and things like that. All right, so this is how you write count change. Okay. Okay, on top. Okay, first of all, what happens here? Okay, this is the deal, right? You basically are writing code, and you're using objects that you didn't write. Okay, in Scheme, you have this thing called requires, correct? Yeah. Okay, so what requires does is that it loads a bunch of things that you can use after that. Similarly, you can in Java you can load objects. So basically the objects are this. The objects are queue and linked list. Okay. Now what are these things? These are kind of identifies the library where the objects are sitting. Okay. We talk about this in a short while. Okay. Now, so essentially what I'm doing here is this. I have two objects that I actually am using. One is actually a queue. The other one is a linked list. Now the queue is actually not an object. The queue is actually an interface. Okay. So what I'm doing is the following. I am creating a new queue. Okay, which is a node. Which contains nodes, okay, and then what it is that it's actually a linked list of nodes. Okay, because the linked list actually implements the queue interface, you can do this. Okay, it's just a system like last time. Remember the singer thing? The singer is an interface. You can then assign something that influences the singer into the thing. Now, okay, what does the node tell you? This is not generics, okay, which means that. Okay, you see the thing about queues is this, right? The queues you can use them to put nodes. You can use them to put numbers. You can use them to put different things. Right. So this identifier here tells you what types of stuff or objects are being put into this queue. Okay. So essentially what I'm saying here is that I can create a new queue which is in a linked list, and this linked list is meant for nodes only. Okay. So obviously what I'm doing here is that now the fact is that the beginning I need to put in the first initial node, right? So I create a new node and I put inside the queue, offer to the queue. Okay? This is actually the code that we saw earlier. Okay? Now what happens here is that what? When the queue is empty, yes. Queue has no constructor, queue is interface. So the queue is not object. The queue is actually interface, which means that it's only a collection of methods, right? So essentially you can assign different. So the linked list is one object that implements the queue. So you can replace this with any kind of. Okay, so the question is why are we doing this? Why don't we just use linked list node? Why do you use the queue node? Well, one reason why we're doing this is because I'm teaching something. I'm teaching that this is possible, teaching about interfaces. Okay, but a more subtle reason for doing this is the following. Now, if the code is written, okay, by using the interface instead of the object, right? What you can do is later on you can happily go and replace the underlying implementation with something else, okay, and the code remains unchanged. So it's kind of cool. Think about it. So it's like you basically have a car, right? With Toyota. Next thing you know, you take out the engine, put inside Porsche engine, and you play the same road text. How cool is that? Yes? Say it again. Okay, so your question, just you understand the question. The question is that now you constructed a queue of nodes, right? And then you basically create a subclass of nodes, call it some super node or something, right? The question here is whether you can put a super node into the queue. Is that right? No, as far as I understand, you can't do that. Right. So that means the question here is whether you can actually change it to super node if super node is a subclass of this. I don't think Java syntax allows that. But I'm not completely sure. But you probably wouldn't want to do that actually. It's kind of odd, right? It doesn't make any sense. But what you can do, okay, is that even if it's a queue of nodes, you can subclass nodes, make it super node or something, and put it super nodes. Why? Because a super node is a node lah. I mean, so you know you can put stuff in there because they're the same type. Okay. On the other hand, if you create a queue for super nodes, you cannot put nodes in there because it is possible that a node is not a super node. Okay. Sorry. You can but then if you screw it up and then it's not really a super node, then you will have a runtime error. Okay. Okay, so this is the algorithm, right? First of all, you check whether the queue is empty. If the queue is empty, what you do, you remove the top element from the queue and you cast it and you put it into this thing called node, right? Okay. Now the node, you check the amount is 0, you add the counter. Okay. If the node amount is less than 0 or the kind is 0, you do nothing, you throw away. Okay. If these two don't hold true, then you do what? You create 2 more nodes and put it into the queue again. So this thing will keep going and then until the queue is empty, right? This is the original algorithm. Okay. Then at the end you return total. Okay. Okay? So this is actually exactly what you saw in Scheme. Alright? Okay, now, so okay, before we continue and people are sleeping already, we will show you some videos. Okay, so today I know it's very tough, so I show you more videos. Oh, wake up. Okay. Korean, because I don't know, they're cute.
ことをそのまま書けばいいんだからね。
Who is Korean? Did you know Korean? Okay, you understand the moral of this whole story, right? So the children were asked to draw an animal, right? Okay, so at the beginning when you asked to draw an animal, right, children will draw Pikachu, whatever lah. Okay, so this is interesting. So I thought it's kind of like a cute short video. It's kind of interesting. Okay, next let's take a look at this. Okay, not this one. Okay, so the question now is this, right? How many of you will make a lot of money? Okay, so this is an interesting guy, okay. Oops.
Today's American Story with Bob Dotson comes from one of this country's best-known addresses, home to some of the wealthiest people on Earth, and a man who has made a fortune selling on street corners.
In the garden of life, big things can grow from small beginnings.
And you make 5 cuts in a carrot. You can all do that.
Provided you use enough fertilizer.
Come up the yard, you'll see better. Come on. Don't worry, I won't ask you for money.
Joe Otis could talk a starving dog off a meat truck.
Now come up round the front, I'll show you how this works.
The man in the $1,000 suit sells $5 potato peelers.
And you turn the whole potato into great French fries.
Very cool.
Lots of them.
There you go.
You won't believe his warehouse.
So where do you keep the potato peelers?
Right in here.
Boxes and boxes in his Park Avenue apartment.
Really?
Yep, Park Avenue.
Never underestimate a small amount of money.
Gathered by hand, 6 days a week, for 60 years.
Now why would you buy 4 peelers if they last a lifetime? Because you've got 4 friends, that's why.
Joe's business makes him something of a mystery man in this posh neighborhood.
Some people suspected that he might be Sean Connery.
Just pull the handle, just try it. He's got an English accent, but he's probably from Mobile to Alabama, who knows?
The accent is as real as the bombs in his boyhood backyard. Joe grew up in Great Britain during World War II, learning from pitchmen who set up in the rubble.
Joe Squinters, Black Douglas, Heckle and Peckle, they were brilliant.
And so, it turned out, is Joe.
Big crowd.
What's the most unusual thing you've sold?
Unusual. Christmas trees in February. I'm not kidding.
Joe taught his daughter Ruth how to hawk children's books on the street, so she could put herself through Columbia University.
What's the key to your dad's success?
Tenacity and patience.
And that's the secret of happiness, not doing what you like, but liking what you do.
Joe lives the kind of life most of us only see in the movies, but he wanted to share it with someone. So he took out an ad looking for a wife, his 4th. He received 600 proposals, picked 3 possibles. The next evening, he met the woman he would marry. She had not seen the ad.
I had the happiest time of my life. My late wife, Estelle.
She died of breast cancer last November. Now he works for the other women in his life, his granddaughters.
Me and my friend went to a river and we caught minnows.
Minnows. I want the kids to go to the best colleges it's possible to go to, and I want to pay for it.
That's why Joe is up before dawn every day. At 74, still pushing potato peelers down Park Avenue.
Do you ever take a vacation?
Life is a vacation. Every day is a vacation.
To be savored. For today, Bob Dotson, NBC News, with an American Story on Park Avenue.
Isn't that something?
I'm a new hero.
No, and slow and steady.
Okay, so anyway, the interesting story is that this guy, he sells potato peelers. He wears $1,000 suits, okay, and he lives in Manhattan, his own apartment, okay, but he has been selling these things for 60 years. So let's just quickly take a look at how he does it. It's kind of cute, okay, so, yeah, just take a look. This guy, so there's somebody filmed him in the act.
Then you hold it in the other hand. You've got those lovely carrots somewhere. Hold it in the other hand. You've got those lovely carrots somewhere. And you do that for the kids, they'll eat the vegetable, I think it's can. When you peel a potato, it doesn't matter whether you're right-handed, left-handed, like a politician man. All you take off that potato, or any other fruit and vegetable, is a thin layer of skin. You've got no weight, you do it back all the time. You come to an eye, you scoop it out, this scoop. Everybody's got one like this, they take too long. Grandma gets arthritis, she can't hold that. She can hold this with one finger. Even arthritis won't stop her peeling. To make really good French fries, use the eye at the side, use your thumb as a stop. You know what makes them so good? They've got 3 sides, so they use less oil. You'll turn the whole potato into great French fries in no time. Hold it in the other hand, it's more than a peeler. That's a mandolin, a slicer. You let those slices go into hot oil and watch them go brown, you're going to love the chips. You hit that bar every time, you get a clean slice every time. You'll slice hard cheese for Caesar salad. You haven't got a knife at home, will make home fries as thin as that. How long would it take to do that with a knife? Now my machine is so gentle, you'll peel asparagus without breaking the tip. I know this is a carrot. You want to see how easy? Just pull the handle away. Try it. Hold it at the side. Look at that. Oh, I'll do it again. You've never used a peeler so sharp or comfortable in your life. I'll show you how you do this. You can have them. It takes a few seconds. First, you peel the carrot, and then you slice it. Now, when you slice, you don't hold the carrot up in the air like when you peel. You put that carrot on a hard, flat surface. You press harder than when you peel. So the slices come out thicker than the peel. You slice hard Italian cheese, as thin as this. Now you put the slices together like a pack of playing cards. You could all do it, but you've got to use at least 6 slices. Don't try this with one slice by itself, it won't work. You fold the slices over. You hold the loose ends in one hand. Now you can see how sharp it is. See, they're made in Switzerland from stainless steel, they cannot rust. They're dishwasher safe, they never need sharpening. And if anyone thinks that's a special one, you can have that one, I'll use another one. This is not TV, this is live. You can't buy them in the stores, they're made in Switzerland, they're not made in China. They're $5 each, they're worth every penny. They last a lifetime. And if you buy 4 for 20, you get 1 free. You want 2. So you get 1 for 5, you get 5 for 20. I know you don't need 5 peanuts, but next week you'll need some gifts. And when you give that as a gift, you're giving them something they can't buy in any store. How many? 1 for you. They're going to dig up you every time they set foot in the kitchen. How many? You want the 5? You only want 1, you got no friends like me. 1 for 5, 5 for 20. The best $5 you'll ever spend. They're not cheap. Nothing from Switzerland was ever cheap. Think of the Swiss Army knife. You're not buying these because they're cheap. You buy them because they're good and they work. If you want to buy cheap, you get one of these in a 99-cent store. They're no good, but they're cheap. They don't do anything.
No, he doesn't. He doesn't make the machine. He just sells them. Okay, actually, there's another cool video of the daughter doing this. Actually, it was really cool because it's exactly the same as the father. Okay, I don't know where it is right now. Okay, but I don't know why it's together with the Guinness World Record of this bra thing. So strange. Yeah. So anyway, the funny thing is that so this is a story of success without going to school. Right. So obviously, it's kind of cute, I mean, the fact that this guy is selling potato peelers, on the street sidewalks of New York, and he's basically richer. I mean, he has a $1 million apartment in Park Avenue. But the interesting to note is that he's good at what he does. Okay, you saw how he does his sales. It's kind of cool, right? And the other thing is really that he basically doesn't take vacations, right? So he works 6 days a week. I'm not saying that you should also work 6 days a week and not take vacations, but part of success has to do with tenacity. Basically, you're able to take shit. Okay. All right. So, any questions? Okay, if not, we continue. Those of you who are interested, you can go and check it out. There's a video of the daughter doing this sales. It's very interesting. After you see the father do the sales, right, you see the daughter doing the sales, and it's like, wow, there's an art to it, right? And she does say exactly the same things, exactly the same. That's exactly the same actions, right? It's quite interesting. And obviously, my view is this: the peelers are really not that good. The fella is just really good at the peelers. Okay, I'm absolutely sure that if you buy the peeler, you do the same thing, you can do what he does. But after 60 years of peeling, I'm quite certain you get pretty good at it. Okay, so this is interesting. This is sales for you. All right. So the moral of the story is this. Okay, now we're going to continue back to the story, which is that we don't reinvent the wheel, because the point is that many people can use the same code to solve the same problems, right? Okay, except maybe this wheel. This is a really cool wheel that somebody invented. What does this do? This is really a jerry can, which means that it carries water. Okay, so the problem here is that in many third world countries, right? Basically, like you, they don't have taps. They turn on the tap and the water comes out. They actually have to go carry water, right? And it turns out that water is a bit heavy, right? Okay, so some fella was really quite smart, I thought, right? He basically created a jerry can of this shape, right? So you fill out the thing, and you basically use some kind of a rope thing to just drag it, and it rolls along, behind you. Huh? So I mean, I thought this was kind of interesting, and it's like so damn obvious that why didn't they think about it? But it's kind of cool. So this is actually what it really is a water jerry can, except it's round. Okay. So anyway, this is random. Okay. So the point is this. Suppose the fact is that we want to write code now. Okay, we write code then we know we might get reused later. So how do we deal with this? Okay. So the general idea is that you will write this thing called software libraries. Okay. Java obviously comes with many libraries. So the question now is, how do you deal with these libraries? Okay, so the main problem is this, right? The problem with libraries is that you can write a queue, I can write a queue, and then at the end of the day, there are a lot of people writing same code, right? And by principle, two pieces of code will have the same name, right? So along the way, I mean, you get enough people, you have this problem, right? So the point here is that you basically will have this naming conflicts. Okay, so the question is, how do we deconflict? Okay, so first of all, we can obviously avoid global variables. Okay, but that's not so simple. Okay, it turns out that most or all modern languages actually have libraries that we included. Okay, and there's ways to deal with this. Okay, so the problem is that avoiding global variables is not good enough. It just turns out, because sometimes cannot be helped. Okay, so the general idea is this: is that the languages will have some kind of convention. Okay, and if you follow the convention, then things will work. Okay, and this is the convention of Java. Okay, so there are two things that needs to be sorted out. Number one is, where should the library file be kept? Right, because the code must be kept somewhere so you can call it. Second thing is that, how do you name it? Okay, how do you address this object? Okay, so the Java convention is to use reverse domain name. Now, suppose I own this thing called benleong.com. Okay, now let me just go back to the history of Java. Okay, Java, by the way, was invented in when? 1995. Wrong. Okay, so the reason why I know this is because I'm one of the first two Java programmers in the world. Okay, I went to MIT in 1993. Okay, Java was actually released in my sophomore year. So when I was second year in college, I was one of the first two people in the world to program in Java because it was new. I was it sounds cool, but it's not cool. Okay, writing in a new language that just got invented isn't that cool. Okay, so now Java is 6 or 7. I think 7. I can't remember what. 6, 7. I know what version it is, but the point now is that in 1995, it was actually 94, 95. It was invented and released, right? And the original intention of Java was supposed to be what? Some web language, right? Basically, the whole point was this applet thing, whereby you can basically go to the web page, and then the web page will deploy you an applet, and you run a program. Okay. So the point is that because of this kind of history, right? There's this kind of idea, essentially you own some domain, okay, and essentially your domain is kind of used to identify the objects. Okay. So it turns out what happens is this now. The domain then is reversed into a directory structure. Okay. So benleong.com becomes com/benleong, right? Because directories are that way, right? Okay. And obviously the point is this: the obvious idea here is that because domains are controlled, if I'm benleong.com, you can't be benleong.com, right? So that obviously then the fact that where the objects come from will basically deconflict the objects. Okay. So essentially this is how it works now. Okay. And the variable names are obviously the reverse of the domains. Okay, domains will be something.com. This will be com something. Okay. So the idea is that suppose I have this thing called cool object, okay? What I will do is that I will probably have a subdirectory under com.banleong.cool, okay? That means what happens is that in my site, I will have a directory called cool, right? And then essentially inside there I have all my cool objects. So basically this thing, okay, cool, a directory of stuff is a package, okay? And essentially this is an object in a package. So you can either load an object, one object on a package. It means if you do import com, banleong, whatever, cool objects, then once you have this line, in the subsequent code, you can use cool objects as a type. Okay. Now, if you do import com, banleong.cool.star, basically I'm importing all the objects in that package. Okay. So once the object is imported, right, you can be used just as a type. Okay, and you can basically call it. All right. And the way that it works is that I'll talk about this next week in more detail. But the idea here is that if you write code as a package, right, you can basically have a kind of identifier called package that basically allows you to declare that this object is a part of this package. Okay, so this is the general idea on how to use. Okay, now next. Okay, so the Java collections framework is actually a package that contains a lot of data structures that are often used. Okay, so a collection is really a collection of objects. Okay, so essentially what you want to do is a container that is used to store multiple objects. Okay, and collections are used to store, retrieve, manipulate data. Okay, so basically, okay, next semester is when you learn to write data structures, 2020. Okay, it turns so util is one of them, and under util you have all the collections framework objects. Okay, there's Q there also. Okay, so inside the collections framework consists of three different things. Okay, first thing it consists of will be the interfaces, which are queues. There are implementations of interfaces. Okay, linked lists, all kinds of lists. There are also algorithms. Okay, with the algorithms that they can do things like binary search and things like that on the objects themselves. Okay. And these are polymorphic algorithms because they can actually be applied to different implementations of the appropriate interface. Okay? Okay, it turns out this is a very huge thing. And this class, I'm not keen to tell you, teach you about this framework. Okay, what you can do is you go and Google Java Collections Framework. Okay, there's probably an online tutorial, there's all the Java docs, you can go read. Okay, so just know they exist. Now, these are the common data structures. Okay, linked list, array list, hash map, hash table, and things like that. Now, okay, I know you all are very, very fond of lists after this class. The equivalent of lists in Scheme is linked list. Okay, but this is something you never want to use in Java. Why? It's very slow, typically very slow. Okay, what you want to do is typically use array list. Okay, so in Java you will never use linked list. Almost, I never see a reason to use it. Okay, you almost always use array list. You are. Because sometimes it's convenient to have a list. Oftentimes it's convenient. For different operations, it's convenient to have a list instead of using an array. One thing that a list can do, it can almost infinitely add stuff to it. Array list is a list that's backed by a array. Okay, next semester hopefully you learn how to do this. Okay, but the idea here is that the general idea of array list is that it's a list. Okay, but the internal data structure is actually an array. Okay, now problem with arrays is actually that they are fixed size, right? So what really happens is this: you add stuff to it, right? At some point, run out of space, right? What the data structure will do is that you will actually basically create a bigger array, copy all the old stuff over, and throw the old one away, and then you get bigger. So it means it takes care of all the array expansion stuff that you may need to do if you have to do your own array. Okay, typically you double the size. I don't know the implementation, but I don't really care also. All you know is that it's typically faster. Okay, linked list is a bit slower because to access elements inside, you need to actually go down the links, which is kind of slow. Okay. Now, so let's quickly talk about hash set, hash set. Okay. The problem is this. Remember, in so far, remember we had this discussion on what memorization, right? Memorization means what? You need to basically remember stuff you've done before. So this only helps if you are fast in checking whether you've done it before or not, right? Okay, think about it, you're doing this memorization operation thing, right? Whereby basically you are doing stuff, right? Then every time you compute something, you put inside, you store in the table, right? And then before you actually compute something, you check whether the table exists or not, right? Whether it exists in the table. But if it's checking the thing in the table is damn slow, then it's back to square one, right? Okay, so it turns out that there's this idea, okay, and you definitely will learn next semester, I think, which is called hashing. Essentially, you take an object, you use a random operation to it, generate some number, okay? And basically, what you do is that a table is organized in the form of buckets. So probably some modulo or something, okay? So maybe modulo, okay, so if you want to have 10 buckets, what you can do is that you can do modulo 10, and then basically depending on which, you take the object, you hash it to some number, okay? And then you do modulo on it, and then just the modulo, you go into the right bucket. Okay? Now, what's the point? The point here is, obviously you may not have 10, you may have 2,000 or something. 2,000 or 3,000. Okay? Now, if your objects are small in number, let's say, your hash has 3,000, your objects are only, I don't know, 5 or 6. With high probability, every object is in one bucket only, and one bucket only one object. So the whole point here is that then the access will be very fast, because you can check whether it's inside there using one lookup. Obviously, if you have 2 objects in one bucket, then it takes a bit longer, but it's still small. Okay, so the idea of hash table is this. Now, so what's the problem? Now back to the original point about hash code, right? Okay, so this is a subtle point. So the idea of hash tables is that you take an object, you do a hash function of the object, which is a hash code thing, you get some number, and this is the number, you do some modulo thing, you go to the right bucket, right? Okay? Okay. Now, remember, the default object hash code is some random function of the memory location. Okay. So what is the problem? The problem here is that you define a new object. Okay. And use the new object is used as the key. This is a key for a hash table. So the idea is that you hash basically where you put the object is actually the hash of the key. Right? What happens is that you are using equivalent objects. That means it's like vector 1, 1, vector 1, 1. Okay? If you basically have different hash codes, that means when you hash the first object, you go to one bucket. You go to hash the second object, you go to another bucket, then basically your hash table goes haywire. So that's why it's important to override the hash code so that equivalent objects, okay, will have the same hash code. This will make sure that the hash table operations are all correct. Again, this sounds very obscure right now, but let me tell you, if you don't do this properly and you have a bug, my God. How do I know this? Because I committed this mistake before. I tell you, it is a disaster, okay? Figuring out that your things are blowing up because the thing hashing the wrong places is not the funnest thing on earth. You will use it at some point, you write enough code, okay? My point to you is that I'm telling you this stuff because it's important, because I have committed mistakes before. I have had a bug one time whereby I created a new object. I forgot to override hash code. My God, and the debugging, I tell you, was a disaster. I eventually debugged it, but after I want to kill myself. Because it's really hard and obscure to find. Okay, it's not your ordinary kind of bugs, no, because it's really obscure. Okay, so I'm telling you this basically to, okay, some of you will understand, some of you not understand, but it's okay, I try my best. Okay, when you get screwed over one time, you will confirm understand. Okay, very well. Okay, because you will spend like hours trying to figure out what the heck's going on. No, because it's completely obscure, and the problem with hash code is that it's a bit random. Sometimes it actually works, no, if you're lucky enough. It has some weird property, like it's a bit non-deterministic. So it's very, very hard to, because the problem now is that the default hash code is random. Right? So every time you hash, there's some different behavior. So it's really nasty. Okay? But you figure it out, okay? So the thing about all this Java collection framework is that please go and check the API online, look at tutorials, and next semester you all will be doing more data structures, so you'll be fine. Okay, so collections can only contain objects. Okay, the thing about this thing is this: all these primitive types. So primitive types can't really put into objects. can't really put into collections. But it turns out what happens is this, Java has got this wrappers that allows you to wrap the primitive types, so you can put the primitives into the collections. Okay, this is a bit obscure. Okay, again, why it's like that? It's historical, because when they first designed these things, Java evolved. Right, so since 1.5, you don't have to worry. Since 1.5, the compiler itself is smart enough to recognize some wrappers. Last time it's very nasty. Last time you have to basically figure out whether the thing is wrapped or not wrapped, and then you unwrap. If it's wrapped, you must unwrap the thing yourself. Now you just basically interchangeably anyhow use, whether it's a wrapped object or the primitive, the compiler will figure it out. Okay, so this is something you don't have to worry about, but you must understand that when you put you can put primitive types into collection objects, but they'll be wrapped, okay, automatically. Okay, so okay. Now prior to 1.5, it turns out that the collections are untyped. Means you can do this, and then you can put anything inside the queue. Okay, you can put anything inside. Now generics are introduced in Java 1.5, which is this thing. Remember, I told you the typing thing. Okay, so now with this typing thing, right, you can put ban into the queue. Okay, now the difference is that in the first case, okay, in the original case, all right, after taking ban out of the queue, I have to cast him as a singer before I can assign to ban to ban. Because the problem here is that in the old version before 1.5, the only things that put into the queues are objects. So you take out as an object. So in order to assign an object to a variable, you need to actually basically cast it. Now, ever since the 1.5 and you do this generics, right? Okay, you don't have to. You can just basically take it out of the queue and put it inside. It's fine. Okay. Now, can you do the old stuff in the new version? You can still do it. Actually, I think you used to be able to do it. Just that you have all the compiler warnings. Okay, so if you do something like this, you can probably still do it for, I think, backward compatibility, but you get compiler warnings. So you should not do this ever again. You should always do this. Okay, and then the point now is this: you can even just do queue.pick.sing. Okay, because the fact is that the compiler knows that the queue contains singers. Okay, and so anything that you can pick out, it can sing. All right, so this is possible. All right, so the last thing I'm going to do today, okay, is dynamic programming. Okay, now I don't know how well you understood the lecture in Scheme. So basically, what I'm doing now is I'm doing revision of dynamic programming. Okay, and it turns out that dynamic programming is much more, I think, much more intuitive in imperative languages than in Scheme. Okay, because it's more intuitive. Let's take a look. Okay, so count change. Okay, this is the general idea lah. If you can solve something by memorization, you can definitely solve by dynamic programming because they are sort of equivalent. Okay, so what we do is we just saw count change earlier, which is what we discussed many times. So now we will now look at how to solve count change using dynamic programming. Okay, so there are a few steps. Okay, so these are the steps. Okay. First thing, all right, you must figure out what a computation is and what is the state of the computation. How to represent the computation in terms of states. Okay, count change. What are the states? Two things, the amount of change and the number of types of coins available, right? These are two states. Okay. Next, you must identify the recursion, which obviously you know lah. Recursion is the base case, everything. Base case recursion, right? Next thing you must do is set up a table. Okay. The table is set up is obviously determined by the state, right? So in this case, you have amount and you have what types of coins, right? So obviously it's a 2D table. Okay, one is amount, one is type of coins. Okay, and then figure out. Then the next thing is to figure out how to fill the table to the required values. See, the point here is that this table is set up, right? How it works is this: you figure out what are two axes. Okay, the base cases were basically initialized like normally two rows, the top row and the side row. Okay, and what happens is that the recursion is used to fill the other entries in the table. Okay, we will see in a short while. Okay, so quickly overview. State of computation obviously is AD, two things. Okay, and then recursion is this thing, right? The recursion is very simple. Basically, the number of ways is number of ways without using the biggest denomination. Okay, and number of ways using at least one of the biggest denomination. And if you use at least one of the biggest denomination, the amount will reduce by the denomination of the biggest denomination, right? Okay, so this is the recursion. Next. Base cases, you know this tree, right? Very, very straightforward. Okay, now, So next thing you do is set up a table, okay? So the idea here is that the table looks like this because there are two axes, two states. One is the number of denominations, one is the amount, okay? Horizontal axis, horizontal is the number of denominations, and the vertical axis is the amount, okay? So basically I see nothing means no denomination, 1 means only 1 cent, 1.5 means 1 cent, 5 cents, and so on and so forth, okay? Alright, now, obviously, there's something you need to compute, right? So essentially this means what? This means you want to compute count change 8.3, correct? Basically you want to compute how to change $8, 8 cents, using 3 denominations. So the idea is this, right? The idea here is that you want to fill the table until you reach this value. Once you reach value, you're done. Alright, this is the general idea of dynamic programming. Okay, so you figure out how to fill this. Now, the first thing is the base case. The base case typically will fill up one column, one row. Because this is like how you initialize it. This is like the ends, right? Now, then the next thing is you use the fill sequence. So the next thing is based on the recursion. Okay, you must figure out how you want to fill the table. Okay, that's the general idea. Okay, so in Java, what you can do is that you can use a 2D arrays. So arrays are kind of nifty. Okay, you can have 2D, 3D, 5D arrays, whatever. Okay, so here what you do is use a 2D array, and what we will do is use 2 loops, inner loop and outer loop, to essentially go and loop through these things. Okay, to reach this value. Okay, so you know something, that each new entry is really the sum of what? 2 previously computed entries. Okay, now how does this work? Okay, suppose you want to do what? Count change 1 cent, okay, using what? Only one denomination, 1 cent, okay. This value is what? Is the sum of using at least 1 cent, which means that once you use at least 1 cent, you basically have no amount left, right? Okay? And not using 1 cent, which means that you got no denomination, which is 0. So this is the sum of this and this. Okay? Now, what is this? This is you're computing A, which is what? Which is 1 cent total, using 2 types of coins, 1 cent coin and a 5 cent coin. Okay? Now, you can do 2 things, right? You can either not use the 5 cent coins, which gives you one way, or you can use at least 1 5 cent coin, which basically gives you to negative something. So negative something, this thing, okay, I didn't draw this rows here, but this number is obviously 0. So 0 plus 1, answer is 1, right? So you can do this. Now look at this thing again. This one, okay, so suppose you have 5 cents, okay, 5 cents, and you want to compute number of ways using 2 denominations, 1 cent and 5 cents, okay? On the left side, what is this number here? This number is the number of ways that do not use the 5 cents, which is 1, alright? You add that to what? Number of ways of using at least 1 5 cent, which reduces the amount to 0, okay? And basically the ways is 1. So total is 2. So essentially, by this method, right, you will basically be filling up the... So essentially what you do is that you initialize all this to zeros, all this to ones, all this here is all zeros, and essentially you will fill up this way, right? Okay, that means the point here is that you visualize this, you know you're filling up this way. Am I clear? Okay, can you fill up the other way? Okay, but normally there may be more than one way of doing it. Okay, so you can probably fill up the other way, but now I will fill up this way. So let's take a look. Okay, this is how I will example code. So first of all, okay, just now I showed you this thing called the lookup table switch, right? Waste time. So what I'm doing now is that I'm doing this thing called denominations. My array is called denominations 0, 1, 2, 0, 1, 5, 10, 20, and 50. Okay, so I use array to create denominations, and I use a static array, whatever. Okay, so I just instead of doing a new and everything, I initialize the array directly by using this notation, using the curly braces. Okay, so basically what this will do, the norm will be how big is the array? The norm will be a 6-element array, right, consisting of 0, 1 to 50. Okay, next, then the procedure is called count. Okay, count 2 things, amount and kind of coins. Okay, and what I do is now I create a new AD is this table, AD. Okay, it is the 2 square parentheses. Okay, which means that this is a 2D array, okay? And I create a new 2D array, okay? First array, the first axis, the x-axis, wrong. Okay lah. This is actually the y-axis, so it doesn't matter what you call it, but the first thing is amount, and second one is the kind of coins. And I do amount plus 1 and kinds of coins plus 1. Why? Because actually I only work with 0, right? If you take a look at the table, right? Actually, the table, okay, here is actually 8, 3, but there are actually 4 columns, and there are 9 rows, because I need to add a 0. Okay? So essentially the table, the array needs to be amount plus 1 and kinds plus 1 big. Okay? Now, so I have 2 loops to fill the table, right? Now, obviously, I have to decide, this is I and this is J, whatever lah. Okay, just call, you need some kind of variables, okay, to basically do the loop, right? So what I'll do is that, because I'm doing what? I'm doing this way, right? Correct? Okay? Now, typically, the convention is that IJK, these are 3 kind of, I don't know why we use IJK lah. For some strange reason, IJK are the typical looping variables. Okay, I is an outside, and then you go IJ and K lah. Okay, so I is the first variable which I use to go this way. K is the variable I use to go this way. Follow? Okay. What? J. Why J? Yeah, I and J lah. So I is this way. Okay. So I is the denomination. So the denominations goes from 0 to less than equal to number of kinds of coins. Okay. Then J is the internal loop which goes from 0 to the amount. So essentially, the outer loop goes this way, inner loop goes downwards. Okay. Now then, every time I go inside, I fill, right? Now if I is 0, I will fill the zeros. Okay. If J is 0, I will fill 1s. Okay. Then else what? If the denominator I, this is what? Basically, if you need to compute something upstairs, I will ignore one piece, right? If not, then I will do the recursion. Basically, A D J I is equal to this is the recursion, right? Basically, yeah, this 2 things gives you the number of coins, number of ways not using this coin, and number of ways using at least one of these coins. Okay, all I need to do is make sure that this part takes care of the fact that the denomination is so big that you go up into this space, and then that one I just throw one away because it's 0. Okay, and then essentially the point is this: once I finish these two loops, inner outer loop, right? Once I finish the loops, then the whole table is filled up. Okay, and what I do at the end is I just return AD, amount, and kinds, because I know that by these 2 things are finished, this entry is filled, and this entry has the correct number. Question? Okay, so the last time maybe I wasn't so clear in terms of the dynamic programming for scheme, because I was also a bit sick that day. Hopefully this is much clearer. Okay, are we clear now? Yes. Amount plus 1. It's amount because the size. Okay, the array is indexed from 0, so it fits very nicely. Okay, now this code is definitely correct lah. Okay, because confirm right, and I mean the code is really written. Okay, so this ends pretty much the dynamic programming. This is something you need to know. Okay, at some point in life lah. Okay, hopefully you understand. So this gives you a good overview of how it kind of works. And the key thing is to understand the big ideas. Okay, it's really not very hard. Okay, dynamic programming sounds like a big word, a very scary word. But it's really quite a simple idea. You figure out what a table is and fill the done table. I mean, that's really the general idea. Okay, so the hard part is figuring out what the table is and figure out how to fill. I mean, but if all things life is complicated. Okay, now last thing. Okay, now next question is, okay, so I've shown you how to do dynamic programming in Scheme, memorization in Scheme, right? And then I've just done dynamic programming in Java. How would you do memorization in Java? And this is something that I will not cover in class. Okay, so go and think about it and hope that you think hard about this. And with that, I thank you very much for your attention. Yes, question, last question? No, you will not need to use all these libraries. How cool is that? Practically nothing, but maybe I covered in lectures is sufficient, guaranteed. No, but the lectures I cover, okay, but I don't cover enough. Okay, so answer is no lah. Okay, any other questions? Alright, if not, thank you very much. I will see you in, there is recitation today, Okay, I'll see you in a few hours. Bye-bye.